Welcome DKP Sogong aboard. Your learning journey starts now. Ever felt like some problems are just too easy to check, but impossible to crack? That's the heart of P versus NP. We know how to verify a solution lightning fast, that's NP. But can we find that solution just as fast? That's the million-dollar question. The real kicker is this: we only see the problem X, not the secret witness W, that makes it true. Can we even tell if such a witness exists just from X without cheating by looking at W? And can we do it efficiently every single time? So what's the deal with these witnesses? Think of the witness fiber F sub R of X as the entire collection of possible secret codes W that work for a given problem instance X. For NP, if someone hands you a code W, you can quickly check if it's valid, easy peasy. But P demands something more. You need to look at the problem's X alone and decide definitively whether any such code exists or if the fiber is completely empty. Just knowing there's a code isn't enough. You need to know if one exists without being told. The big warning here? Just because each individual code is small doesn't mean you can efficiently summarize all possibilities or rule them out uniformly. Projection hides the witness, but it doesn't automatically make the hidden complexity disappear. Now let's get a bit more formal, but stick with me. In complexity theory, abstract order isn't just about layers, it's about dependencies. A witness variable might influence future choices in ways the projected input X doesn't fully reveal. To handle this, we introduce residual relation congruence. Imagine two partial solutions alpha and beta. Are they truly equivalent? Only if, no matter how you extend them with any remaining variables gamma, they lead to the same outcome. If they ever diverge, you can't just lump them together. This leads to semantic freedom with, basically, how many distinct types of environments do you absolutely have to keep track of to stay faithful to the original problem? Our goal is to show that sometimes this number is just too large to manage within polynomial time, even for deciding existence. Okay, here's where things get really interesting. We can prove that representing the entire witness fiber exactly often requires exponential resources. Think of covering a complex shape with rectangles. If the shape is intricate, you need lots of rectangles. For certain NP relations like Cyton formulas, this rectangle count blows up exponentially. However, there's a crucial twist. Just because the full map is huge doesn't mean finding your way on it is hard. Take Cyton systems, their solution space can be exponentially complex to describe, yet you can decide if a solution exists in linear time using parity checks. So proving that describing the whole fiber is hard doesn't automatically solve P versus NP. It shows that compilation is tough, but existence decision might be easier. This forces us to zoom in on the core challenge, proving that existence itself cannot be compressed under uniform polynomial bounds. So we've reached the crux of the matter. The ultimate prize is an existence semantic incompressibility theorem. Can we prove that for some fundamental NP-complete problems, any algorithm trying to just decide if a witness exists, operating only on the projected input X, must inevitably require superpolynomial resources? This is the bottleneck. We've identified major obstacles like relativization and natural proofs, and laid out specific tests to scrutinize any proposed proof. The final hurdle is connecting this semantic argument back to standard Turing machines and circuits. If we can bridge that gap, we might finally answer the age-old question. Until then, the quest continues.